Hi, welcome to this lesson on Euclidean geometry, circle theorems, the center to chord and converse theorems. So essentially there are three theorems here for the circle theorem relating to centers and chords. Okay, so the theorem 1 statement is as follows. The perpendicular line from the center bisects a chord. So as we saw in the structure of theorems, there's an if statement and a then statement, the hypothesis and the conclusion. The hypothesis part here is that you are given a perpendicular line that is drawn from the center of the circle to a chord AB inside the circle. So that is what we assume to happen. That is what we assume has happened and is true. The conclusion part is that we want to show that the perpendicular line that we drew to the chord bisects the chord. So what does that mean? It means it cuts the chord in half. Okay, so visually what does this look like? So here's your circle with center O, and we draw a perpendicular line down to some chord AB on the circle. The theorem then says that once you touch the chord from that perpendicular line, there's the 90 degree, then the chord AB is now split in half from that point that you have made contact to. So therefore we are saying AC equals BC. That means it bisects the chord. So how do we prove this? So again, like we saw in the structure of theorems, we take the hypothesis, we assume it all to be true, we do a clever construction given the properties of the hypothesis, and then aim towards the conclusion. So the proof was started as follows. Let OC be the perpendicular line drawn from the center O to the chord AB as follows. So this perpendicular line here. The construction part now, the clever part for the proof, is that we're going to construct two new lines. This is essentially the essence of geometrical proofs, is a smart construction on the diagram that'll enable us to get towards the conclusion of the proof. So in this case, we construct lines OA and OB. There is your construction part. So here are the lines, but OA and OB are radii lines. Okay, so each line is a radius. Therefore, if we call this length R, for example, this length would be R as well. Now we have two right angle triangles. Okay, so in triangle OCA, right, the angle C is 90 degrees because we have the perpendicular line drawn already that was given, because OC is perpendicular to AB. There's your reasoning. And similarly in triangle OCB, angle C is also 90 degrees for the same reasoning. Now OC is a common side to both the triangles OCA and OCB. Okay, so what are we getting towards here? Well, we have successfully shown that triangle OCA and triangle OCB are congruent triangles. So what does that mean? That means that by right angle, hypotenuse, and side, that criteria for congruency, the triangles are essentially identical. They are the same triangle. Okay, so because they are congruent, that means that the lengths sides AC and BC must be equal by congruency of the triangles. But that is what we wanted to show in the first place. So therefore, we have proven mathematically that the perpendicular line from a center to a chord bisects the chord, cuts the chord in half. So what did we use here? We used the properties that it was a perpendicular line to get a right angle triangle. We then created a smart construction, the two radius lines here. And then from that small construction, we used existing mathematical properties that we know already. In this case, congruency of triangles. We use congruency of triangles to show that the triangles are identical, and therefore the two remaining sides here must be equal in length. And that is exactly what we wanted to show. Okay, so that is the proof of the theorem that a perpendicular line from the center point to a chord bisects the chord. Next, we have the converse of the theorem. That is, a line from the center to the midpoint of a chord bisects the chord perpendicularly. Okay, so what does that mean? So the if statement now, so the converse, so we proved P implies Q, where P was the fact that it was already a perpendicular line, and therefore it bisected the chord. But now we are going in the reverse direction, which is called the converse of the theorem statement. So now we want to assume that there is a line that cuts the chord or bisects the chord, because we are saying that the line from the center to the midpoint of the chord. So it's already cutting the chord in half. We then want to show that this line is perpendicular to the chord. So we want to show that it actually is a 90-degree here. So how do we do that? So again, we let OC be a line drawn from the center to the midpoint. That means we already have that AC equals BC. That is the hypothesis part. We are trying to show that this must be a 90-degree triangle now, okay? Because then we have a perpendicular line, and that's what we're trying to show. So again, the clever construction is to construct the radii lines, OA and OB. Now, in these two triangles, again, we have that OA and OB are equal because they are radii, and all radii in a circle are equal. We have OC being a common side to both triangles in length, and we have AB, or AC equals BC rather, and that was given in the hypothesis of our theorem statement. So we therefore have the triangle OCA and triangle OCB being congruent here. So the congruency that we are showing is that all three side lengths are equal, okay? Now the congruency of these triangles therefore implies that angle OCA must equal angle OCB. Okay, so we're saying angle OCA, which is this angle here, must equal angle OCB, which is that angle here. And that is by congruency of the two triangles. But we know that chord AB is a straight line, so another a geometrical property that we are using. Therefore, the two angles that we are adding up must be 180 degrees. But we are saying that these angles are equal. So we're saying what two angles that are equal must add up to 180 degrees. So if you both let these angles be x, then we have 2x equals 180 degrees. Then dividing both sides by 2, we get x equals 90 degrees. So each of these angles must be 90 degrees. So we've successfully shown that the line OC is in fact perpendicular to the chord AB. Okay, so that's how we would prove this theorem, the converse of the perpendicular line bisects the chord. This theorem would be that a line drawn from the center to a midpoint of a chord actually is perpendicular to the chord. Lastly, we have a third theorem about centers and chords, and this is a less well-known one, but we will go ahead and show and prove it anyway, and that is the fact that the perpendicular bisector of a chord actually passes through the center of a circle. So here's the if part, the hypothesis. You have a line that is perpendicular to a chord AB, and it bisects that chord. So we take any line, and from a chord AB, we take from the midpoint of the chord, and we just draw a perpendicular line upwards. What we will show is that this perpendicular line has to pass through the center of the circle. It can't do something like this, for example, and just miss the center and still be perpendicular. That can't happen. So let's go ahead and prove this. So what we will do is we'll let the line DC be a perpendicular line drawn from a midpoint of the chord AB. Okay, so we have the chord AB, the midpoint here, which implies that AC equals BC. From that midpoint, just draw a perpendicular line upwards. Okay, we don't know if it passes through the center yet. We want to show that it passes through the center. So we'll just call the point D anywhere inside the circle that joins this perpendicular line up here. Now the clever construction occurs from extending the point D to another point E in the circle upwards. And then we will construct lines from the endpoints of the chord to both D and E. Now again, we don't know if D or E are the center points. We just know that they are 2 points in the circle that happen to lie on this perpendicular line. So let's compare the two triangles now. In triangle ADC and in triangle BDC, what do we have? Well, we have AC equals BC, that's the midpoint. We were given that in our hypothesis. DC equals DC, it's a common side to both triangles. Okay, and then angle ACD and angle BCD is 90 degrees. We were given that this line is perpendicular to the chord. So by side angle side, we have that the two triangles ADC and triangle BDC are congruent triangles, side angle side. So this implies that these triangles are identical. Therefore, we have that this line AD must be equal to this line BD by congruency. we can extend this idea similarly to the larger triangle. So again, we have AC equals BC given by the hypothesis. EC equals EC, so this longer line now is equal, it's a common side, and there's a 90-degree angle between ECA and ECB, again given from the hypothesis. So again, this shows side angle side that these two larger triangles now, so these ones here in blue, these two larger triangles are congruent triangles. So therefore, EA now must equal EB, or BE equals AE. So what have we shown? That no matter where we place a point on this perpendicular line here, any points, D, E, any point, we can keep showing that the distance from the endpoints of the chord to any points on that perpendicular line are always equal in length. Okay, so that means all points on the line, on this perpendicular line, are equidistant from A and B. So the center of a circle, right, let's call the point O, also has the property that the distance from that center point to the chord points A and B are also the same, the radii lines. So the center point O must also be a point on that perpendicular line, because it satisfies what we've seen from these other two constructions, is that no matter what point you put on this perpendicular line, you're always going to have the property that from that point to the endpoints of the chord, the distances are the same. So therefore, the center must also be one of those points on this perpendicular line, because it also has that same property because of radii lines. Radii lines are equal. Okay, each radius, the radii lines, are equal. Okay, so this is a more thought type of proof. We've got to think about it a bit, but essentially what it says in essence is that if you have a chord and a line that goes from the midpoints of that chord perpendicularly upwards, it will guarantee to pass through the center of the circle. Okay, so that concludes the proof of this theorem. So there are three main theorems when it comes to centers and chords. And we'll see right at the end of all these circle theorems, there'll be a nice checklist that we will go through. And we can always use that checklist to check which theorem should I be using when I answer a circle geometry problem. Okay, I'll see you in the next one.